I'm the contractor of Mecca Techs, and we are getting ready for 4 or 5 things in October here. One is the eclipse that's coming up, and then also for the Boy Scout Jamboree on the Ear and the Boys on the Ear and Jamboree on the Internet, which is coming up the following weekend, and a few other events related to technology and STEM. So I realized when I started working on some of these projects, there's one thing for whatever reason I had forgot to include in our curriculum as we're building a base of knowledge in electronics and STEM is harmonics. So today I want to go over some basics of harmonics, of what we taught in the past, and tie it into where we need to be now, this in October, and go into the future. So Elisa, draw A5 wavelength, a sine wave. It's A5. That's the universal tone for our European music enthusiasts and musicians. It's A above middle C. So equals, no, so that equals 440. That's 440 hertz. H, capital H, little z. Okay. So now we're talking the sound of music, the tone of music, the intonation of music. So A6, make it half of that. A6 is 880, so it's half the size. Okay, now above it, write down A4, we're going to do it, equals 220. Okay, now draw a line at the start, a line at the end, a line through the middle, a baseline. Good girl. Now draw an amplitude line, baseline to the high, baseline to the high. All right, baseline to the high.
And draw a line up.
This way. And then one on the other. So all the parameters of a wavelength that you have to learn. The primary two, what you have to do is learn the equation that has to do with the speed of light. So all you have to put in your mind is another magic number. The magic number has to be 300. Write that down. No, make a chart going down. I'm going to tell you, no, well, that's okay. 30 to 300, 300 to 3,000, 3,000 to 30,000, etc., etc. Speed of light is 300, okay? So in the equation, you're going to use 300, but you're going to have the units behind it is right. So it's 300 then meters per second, but 300 what, okay? So it's 300 times 10 to the 9th power. A million is 10 to the 6th power, so 300 million, if I'm right, is 10 to the 9th power, okay? So this is what you're working with, though, in the equation is 300. So put an equation 300 on top. Okay, now put a line and make a fraction of that and put frequency. Okay, and make that equal to, the fraction equals, yeah, okay? And the other part of it is distance. So let's test her now. Don't scratch it, draw a line through it and make that a K. a constant. Okay, so now that's going to stay the same. So change your equation around a little bit, see if you can do it. Frequency comes to the other side and it goes on top, right? Okay, and just take frequency, put it up here. Take this and put it up here.
No, that doesn't make sense.
That's three equations. You take one equation, just start messing around and so on. So, okay, draw a line. Okay, now scratch this out. We just scratched it out. Therefore, now what you can see, there's a relationship between frequency and
right.
distance. Now you can put different things. If you want to put a lambda in there, Greek letters, you can use whatever scientific notation you want. But this is the concept, frequency. So there's a relationship. If k stays the same, which it has to, speed of light doesn't change in space. That's what you have to understand though. We're talking about speed of light in what is called free space, above the ionosphere in space. Come down, you have clouds, you have moisture, you have dust, you've got all kinds of stuff that will change it a little bit. But we're just going to use, or the radio people, 300. Therefore, if one goes up, what's going to happen to the other one? It must come down. Okay, if this is 10, let's say 440. Just put 440 in front of it. Okay. Okay. So 440 goes up to 2 meter, then it's obviously going to change the bottom of that equation. And this is where you start figuring your antennas. So up here now, write down, I was trying to think where to put 1/2, 1/2, 1/4. So most antennas are 1/2 wavelength, 1/4, or 5/8. And you should, you don't have to, but you should tune them. Which means if you want that length, it's got to be correct. If you want 2 meters, it's got to be 2 meters and the frequency has to match it. So you tune the antenna to make sure whatever that equation says or whatever the computer says on your calculator there and so on. Okay? So now we're going to talk about harmonics. We started talking about harmonics. Oh wait, I didn't finish here. This makes it relatively easy to learn the electromagnetic spectrum. 300 is a magic number. So 30 is the lowest tone on the organ I play. Okay, that's the lowest tone that the ear basically will hear, 30 hertz. So they've divided electromagnetic spectrum from there into low frequency, high frequency, ultra high frequency, and then at some point our eyes come in at nanometers and so on. So that's a good way to try to learn how to divide the electromagnetic spectrum from low frequency to very high frequency to ultra high frequency. Those are the two important ones. Many of us have lived through television. Channel 0 through 12 is VHF. 12 and above is ultra high frequency. So therefore, if you look at the old, you might find in the old TVs two kind of antennas, rabbit ears and a circle. So one for one, one for the other. So now what we're going to talk about is where you take this into harmonics. So C, what happened to C? C4. Write down C4 again. Is it there? I don't see it.
What are you talking about?
Okay. C4 is 440. C5 is 880. That is the first harmonic of that A tone. a four-tone, the tuning for all Western instruments, piano, accordion, violin, etc., is A4 around the Western world. That's called your fundamental tune. Okay? And then you have, as you go up, let's go up to A5, A6. What would A6 be, Elisa?
880.
Okay, you double 880. What is it?
You told me it's 880.
Anyway, that's your third harmonic. Everybody's starting to get the concept of harmonic? You never hear a single tone. So what we're talking about in sound is how do you tell a violin, a guitar, a string instrument from a horn? First of all, you tell it by the harmonics. 2, you tell it by what is called the packaging or the envelope. So any of the young people that work on synthesizers, the rock and roll people, understand this well. Okay? So you've got a fundamental tone, then you have many harmonics for a string on a violin, the upper string. Okay? Then you have what they call the envelope. It's going to vibrate, and it's going to vibrate a little bit more, a little bit more, a little bit more, until it goes all the way down all those harmonics. Okay? Then the envelope is going to be what we call decay. If you pluck a string versus bow it. If you bow it legato style, down, or organ style, versus pound the piano, okay? So that's called the envelope. That's staccato. Vibrato, legato, nice and smooth, okay? So it's decay. It's going to have an attack, it's going to decay. So into all these harmonics start coming this envelope, and then how long it's going to last. In other words, it's going to decay like this, or it's going to decay like that, okay? So you can buy a synthesizer, a little cheap one, start twisting all these buttons, and make a sound. I didn't bring it in here, I should have. Can you go out there? There's a book there. You'll see it. For Hammond organ, sitting somewhere on the couch. And it's got little drawbars in. See if you can find it. So what has happened in our world, this is a German accordion. They've been making accordions for 100 years plus, okay? Italians, French, a very good instrument. Nice because it doesn't take batteries, nice because it walks around, nice because it makes a lot of tone, based on tone and so on. So anyway, hopefully she'll find the book. In addition to this first harmonic and second harmonic, there are harmonics that are in the middle, okay? These go back to the music ear of a pipe organ. Big pipe is 16 foot, little pipe is 4 foot. So therefore that's a what? That's a flute. This one is a bass, hard timber. So in the late 1940s, where I grew up in Illinois, outside of Chicago, Dr. Hammond came out with some brilliant engineering data. So what he did is make little tone wheels that went around real fast, like blowing a whistle. It made a tone. So they were called tone wheels. Okay? So but what he did is make several of them in different harmonics, and you pull that little bar down from 0 to 10, 0 to 10, 0 to 4, 0 to 3, 0 to 1, and now you have a slant. So he went through and figured all this out. This is brilliant engineering. And he figured out all this sound based on electronics back then and making electronic sound. Okay? So what he found out was that you have various families of sound. You have a string sound and a brass sound. So now we can make a pipe organ into an electronic organ. Hammond was the first. So then we come out with about 2 or 3 decades of electronic organs, probably in every church in the United States. And you can see what he's got is patterns. This pattern, this pattern, this pattern, and so on. And that's all based on the harmonics that we're talking about. What percent it is, and therefore what your ear tells you. My ear says that's now her playing the trumpet, A4. So all this electronics. So after this electronic ear then, with a Hammond organ went out. Hammond organ, the one that I have in the other room, we sold it to Japan. So the young lady here couldn't carry it. It's too heavy. So now I've been teaching keyboard to senior citizens, and any young person, her, can put it over their shoulder, carry it in with some batteries, and play it. Okay? So in this era of digitizing it and miniaturizing it, we've gotten smaller. So again, we gave a lot of this up to China and to Japan and South Korea. My piano, my front room, looks like a piano, but it's not. It's a MIDI piano. It's all electronics. So to teach the kids then, what we do is we take an instrument like this here, take the electronics that we know, and we use some of our brain power and put an Arduino in there.
Okay.
And then we've got to get the sound coming in. So we have to wire this here up. This is the old way of doing it. Wire, that's the way the Germans did it. This is electronic way now. When this hits here, it also hits a contact there. That contact there talks to the Arduino, and the Arduino talks to a loudspeaker.
Okay.
So now we have MIDI music. Came out in 1982. Interesting enough, it's one of the things that got me teaching music in a university in Texas, and I never took them. I was never in a band, I never took a music course. But I started studying electronics. Along with electronics, just like radio, came music, MIDI. So I studied it well. So now I can make MIDI music on a computer, or I can make it myself. So now, the accordion made in Japan, as we pass that technology to Japan, is called a Roland. This brain power of this Japanese professor, electronic professor, has started Roland Electronics. And for a long while they had the market in almost any electronic music device, keyboard. And what they did, they took his electronics from Japan, went back to Italy, and they make the accordion, all this in Italy, but they plug in just like what we've done here. He electrifies their device. So now most of the professional accordionists that I know in Texas have a Roland accordion made in Italy with electronics from Roland, and they sell for around $7,000 to $10,000. The one that I have, Roland accordion like this here, the real one made by professionals, sells for around $2,000, and I have one in the other room. But what I'm saying is, we can make it ourselves. One of the young girls that was here a couple of years ago, her last project, I can get out and show you, is Arduino. She made a Arduino piano, just with do, re, mi, fa, sol, la, ti, do. So, but the bottom line is you've got to know this harmonic stuff. You've got to know a lot more than just do, re, mi, fa, sol, la, ti, do, C, D, E, F, G. You've got to know the harmonics that go with it, And then on top of it, the young musicians, rock and roll, don't have any problem learning this because they get these synthesizers and it's all on the synthesizer. So I was going to bring one too, but I didn't had enough to carry. We took an accordion too and put a synthesizer in here that you buy from Japan. And now I can synthesize any song. So now we can make a violin sound with this here, or I can make it by pulling all the little buttons, or I can synthesize with it. I can go on the synthesizer and figure out how to get a violin. When I was young, going to a nightclub, for example, or skating rink even, they had organs in skating rinks. I used to marvel before I knew all this, then I did, but I had some young musicians who were super musicians. They would play the organ and they'd push and pull all these. They'd take these and they'd push them, and maybe they change this to that. So all of a sudden you've got a trumpet sound versus a violin sound. And then for mariachi music here in Tex-Mex country, we have violin and fiddle, and we have trumpet for mariachi, 2 trumpets, 5 violins, a guitar, a guitarrón, and a vihuela. So basically, you can start mixing and matching all of these sounds if you know the basic sound. If I know the fundamental of all the overtones, for example, for a violin, I can add the fundamental and all the overtones for a trumpet, and then I double that. Now I've got 2 trumpets. Violin, I've got 5, so I can show you some of the music that my group has danced to around Texas is electronic music. Most of the audience, including Mexicans, don't know that it's not real live musicians. It's a computer playing. And we have these to give out so people want to learn it so they can understand the concept of what we're talking about. So I'll put this down. So in STEM, then the question is, why do you want to teach this under STEM? The reason being is that STEM has become, by nature, by default, STEAM. They've added A. So this concept related to the ears is exactly the same as related to the eye. The wavelength doesn't change. What changes is what God gave us. He gave us eyes, He gave us ears, He gave us skin. Okay? Now what we're doing is we take the eyeball and we make a sensor. This is nothing but a sensor. This is a sensor. And we take all His knowledge and pack it into there. So now we have a camera that's 4K, 1 pixel on that 4,000 pixels becomes one thing. And we've gone over that. People who look at our videos for STEM Sundays on the back, and they're up on YouTube, we went over RGB, okay, and then sRGB, and then LRGB, and so on. So what's coming up that we'd like to